Welcome to this primer on functions. In this lecture, we will discuss the notion of Cartesian products, and all we need is some basic notions of sets and just basically the definition of a function. There is already a primer on sets in the same playlist as this video. You can find it in the description below. And let us get started. So let's start with an example. So suppose we have 4 movies playing in theaters, and we want to record all the possible shows that one can watch in the first 5 days of the week, let's say, and the days are numbered 1 to 5. So what one can do is make a table. One can say that on day 1 one can watch movie 1, or on day 1 one can watch movie 2, or movie 3, or movie 4. And similarly for day 2, day 3, day 4, and day 5. So it becomes a 4 cross 5 table, meaning 4 rows and 5 columns. And the idea of the Cartesian product is just basically a formalization of this. So here is a quote-unquote definition. It is not a very proper definition, but it is the way we think about the Cartesian product of two sets. So suppose A and B are sets, and yes, they are non-empty. I am not writing that. So the Cartesian product of A and B, which is written in this fashion, this is the notation for it. So the Cartesian product of A and B, written this way, is defined as A comma B, where A comes from capital A and B comes from capital B. So all pairs that you can form, where the first entry comes from what we write first and the second entry comes from what we write second. And all such possibilities you collect in a set, and that is what is the Cartesian product. And in our example, what happened was, here we had the days and this was all the movies. That's all. So what is this notation? This notation is this bracket and then two things. This is basically an ordered pair. That's all. Right? So that's the Cartesian product of two sets. Similarly, we can form the Cartesian product of three sets. So if we were given three sets A, B, and C, then their Cartesian product would be all ordered triples. So A comes from capital A, B from capital B, and C from capital C. That is the Cartesian product of three sets, and you can go on. So you can form the Cartesian product of any given number of sets. And the order matters. So A cross B is not the same as B cross A, simply because, in general, it's not equal to B cross A. Simply because when we write ordered pair, the order matters. This is not a set of two things. This is a pair, so it matters what comes first and what comes second. So one cannot just flip the ordering here. Okay, but one may complain that what is this new thing that we have introduced? We have not looked at ordered pairs before, and it seems like we just invented this new word, and ideally everything should be we should be able to define everything in terms of sets and functions, but here we seem to be invoking some other new concept. Formally, one can actually express this in terms of functions. So here is a formal way of looking at elements of a Cartesian product. So if A and B are again non-empty sets, then an element of this thing is, formally speaking, very, very properly speaking, is a function with the domain 1, 2 and target A union B such that F1 is an element of A and F2 is an element of B. So one should be able to relate this with our more intuitive notation. So when we are given this ordered pair, what function do we, if we want to, what function do we think of it as? We think of it as the function which takes 1, 2 to this set to this set in the way where 1 maps to little a and 2 maps to a little b. So to this we associate this function, and whenever we are given any such function, we can get an ordered pair. So this is the formal definition. So this is just a notation for this function, but we do not usually think of Cartesian products this way. Most of the time, most people will think of it as just a list, and that's the more intuitive way to think about it. So you can just play the same game with Cartesian triples and all that I'm not doing. So let's move on. So now let's take a look at a most basic example. So it's the Cartesian plane. I hope these are horizontal and vertical. I am a bit, particular about these things. So I won't be able to sleep at night if I don't make it horizontal. So let me, yeah. Yeah, okay. I mean, this will have to do, I think. So the Cartesian plane, when we say Cartesian plane, we mean the notation is this, and this is all pairs of real numbers. And surely you have seen this in high school. So when we study coordinate geometry, what we are dealing with is the Cartesian plane. Every point in the Cartesian plane is two numbers, one coming from the horizontal real line and second coming from the vertical real line. And this is the formal description of the Cartesian plane. So there is not much to explain here. Okay. This is an interesting example, Boolean hypercubes. So before defining the most general definition or most general instance of this, start with the simplest one. So this is just a two-element set whose entries are 0 and 1, and one can visualize it this way. This you can think of as 0, and the other one you can think of as 1, and we just join a line for visualization's sake. This is just a two-element set, so when we draw a line, we are not trying to say that the elements of this line are here or anything. No, it is just a two-element set, and these are its representing dots. All right, so here is the two-dimensional version. One can take the Cartesian product of this guy with itself, and that we can visualize via this square. So this would denote 0, 0, which I will just write as 0, 0. This I will write as 0, 1. This I will write as 1, 0, and this as 1, 1. So when I write 0, 0 here, I really mean 0, 0. 0, 1 means 0, 1. This means 1, 1. And this means 1, 0. That's just shorthand. So one can visualize this in this fashion. And yes, of course, we can go to 3 dimensions. So this one can visualize in this fashion, and you can label these in the natural way. So this suggests a general definition, which is as follows. So the nth Boolean hypercube. So the word Boolean comes because there are two things here, and hypercube because it is n-dimensional object, meaning it's an arbitrary dimensional object. So that's why this prefix hyper is defined as this. So yeah, when I write this, I mean this is, I should have said this, but this is a shorthand for that, and this is a shorthand for this. So when we write this, we mean take the n-fold Cartesian product of 0, 1 with itself. And this is just a notation to denote this. Yeah, so this is n times. All right. So that's the definition of the nth Boolean hypercube. We cannot visualize it in this way because we are three-dimensional creatures. But conceptually, it's a perfectly meaningful device. And we will look at how this is actually something that we will... This is actually something very, very natural, as in... So, yeah, I mean, we'll look at it in the next lecture. But for now, this is... I will leave it at this. Let me highlight. And yeah, this is the end of this lecture. So as usual, like, comment, share, subscribe, and I'll see you next time.